Thank you, Nick. It's a pleasure to complete this open source activities from the German side. So I think it's really, as Tom pointed out, a new wave we are in, and so it's really important to get those things forward. And I thank the previous two presenters for really paving the way, so I can directly jump into the topic and not explaining all the things about the open source activities. Maybe let me just, because of the discussion for now, allow me a short comment. So there are countries in the world who, where the transmission data is provided to be used by everybody. And I'm coming from a country where grid operators are very restrictive of their data, and it is very questionable if this restriction and confidentiality is really necessary. And in order to bring the Indian power system forward and include all the research institutions who are having great difficulties in getting this confidential data, and where we have spent a huge amount of time just to get confidential data and talk about confidentiality agreements and so on. So think at the beginning of it if it's really necessary to do this a high degree. I don't think that it's really necessary, and so you will speed up the whole community significantly. So that's, as a starting point, very important. And so maybe this is an outcome from this session and maybe even from this conference. So you have seen that we are going towards a significantly change in the power system, though it's not only an energy system transformation, but it's really a power system transformation. And the big challenge is that networks are not the same. So we have a big diversity of difference in the network. And that is what we encountered when we were starting the Panda Power initiative, actually, that we were working with grid operators, especially distribution grid operators. And so we are talking about, in Germany, about 500,000 low voltage grids, and no one looks the same. Huh? And so standard studies take some type models and say, well, we have 3 different types: villages, suburbans, rural areas. And with these 3 types, which do not at all represent this diversity, they are judging about what is going to happen. It's okay to get an idea, but it's not reality. And so we were trying to identify how can we process this huge amount of data. So we are now on the way to truly run with a very high amount of them. So this is really important to come to reliable analysis. So we started this Panda Power activity. So as Tom pointed out, we were very early also in contact with the PIPESAR team, actually, and we're coordinating from time to time. So what we have as a common framework, let's say, we're using Python. So Python is implementation environment, scripting language-wise, with a huge community, very easy to learn. And so everybody who is not yet used to any tools, Python is really a good starting point there. And but there is only little, there has been, no? Now we have Panda Power and PIPESAR, there has been little tools available for really going ahead. And so that was more or less in parallel the same idea we were working on. So we also have both the way of solving power flows and optimal power flow problems, and very special. So why we call it Panda Power is because we use the Python tabular data structure pandas, which is allowing a very convenient and easy to use way to for comparison, including additional data analysis and so on. However, Panda Power is in many ways different to PIPESAR. So what you have seen with PIPESAR, it's focused on energy modeling and very well designed for that. We are coming from the perspective of we are working close with grid operators. We have real data. We have the detailed data with GIS coordinates and each section with the appropriate impedance data. So we take the real and full information, but of course each of the grid operator takes their own implementation, their own tools. There are common ones, not common ones. So we were not able to be compatible, concentrating on a power factory implementation or whatever else. So we developed an own one. So we have converters to integrate the data and run our modules actually, whatever it was built in. Then we have worked on power flow, of course, the power flow solvers, the short circuit calculations, and topology analysis. And so our focus is on distribution system analysis and planning and optimization, where we have this very detailed data and where we have a huge number of data sets. So we are using parallel, so we are extending it, normally applying it on cluster to run many calculations in parallel, also running probabilistic sets and so on. So it's normal in studies we are doing that we run hundreds of millions of load flow calculations in parallel. And so this is designed for, and so we extended high power for that. So that was the original starting point, and also speeded up that due to the implementation. So the basic idea of Panda Power is actually to have an open source set, which you can see here. That includes a number of element libraries. It provides plotting facilities, load flow solvers of different types, optimal power flow, state estimation algorithms, short circuit algorithms, so this is provided in topological graph analysis, and so this is open source, can be used. There's already a quite impressive user community, so there are users around the globe who are contributing and improving Panda Power. So this is very good situation we are in, so it seems to be very attractive there. What we have around that is because we're using that in professional studies and in close collaboration with grid operators, so the tool is already going to be implemented at one large distribution grid operator in Germany, so it's not only a research tool, but it's actually going to be a commercial tool also. So we have an open source core, but of course we have around that a number of implementations that are in that direction also commercialized and can be adjusted very well. So we have converters from all the different power flow and planning softwares. We are integrating scenarios of different types. So this is information about renewable energies, distributed generators. We are including planning rules, planning guidelines from grid operators. Everybody has them in Germany, but they are all completely different. Not complete, but there is not one unique, so each one is unique, and so it needs to be adjusted there. So there are a number of assumptions taken there. So we have three major pillars we are looking at. So one is power system analysis. So we are running several studies in loss analysis, where we are doing a very detailed calculation. It's about hosting capacity, analysis of reliability, so N-1 calculations, for example, analyzing SIDE to see the reliability indices and so on. So this is one pillar. Another pillar is exactly the planning issue. So we have heuristic optimization solvers that are according to a set of future scenario on the grid. They are automatically optimizing the grid with regard to grid reinforcements, including also smart grid technology. We include there, for example, sectioning point optimization, topology optimization, and so on. And we applied also in grid operations. So yesterday Some of you might have seen a presentation of mine where I showed that we are also developing kind of operational tools. We use here Panda Power as a platform for power flow calculation and easy-to-use optimization. So we are running here extensive time series simulation. We can apply local, decentral, or central controllers. So this is part of that. And it is integrated also in our co-simulation platform, Opsim. I presented briefly yesterday. So it has already proved to be a very good solution. We tested it against many professional software solutions. So we have intensive validation tests that it's really doing right with what the modeling is included there. I'd like to give a brief introduction into the Panda Power and then present a little example about calculation of hosting capacity with it, just to give you a very small glimpse into the capabilities that can be done with that. And well, first, of course, we can compare that with a number of other solutions already available, also open source. As I said, we extended Panda Power in the last column with a number of additional elements modeled in order to have a complete modeling picture of that. So these, some of them are not yet available in open source software, only at Panda Power. So this is very helpful, and that is bringing them on the same level as commercial software, actually. One example is a switching model. So if you might have worked with detailed network data, so some network operators have difficulties with commercial software because if they have two buses and they have switches in between, then it's difficult to model the switch from time to time, which means that they integrate impedances in between, and the impedances are very short, and so that can cause convergence problem of the power flow solver. So this is really some problems at time, and so we have designed ideal switches where we combine, in case we have several ones that are actually connected, and we combine them actively. So this is reducing numerical issues very much. Also, if in case you have a switch open, often the buses are or the nodes are disconnected. Even you have an open-end line, and so that can cause overvoltage issues and so on. So we model that in addition, integrating auxiliary buses actually. So we need to have auxiliary buses to model that. The same holds for transformer data. So this is just a small example of what kind of improvements are in there. So I think I talked about those things. So there's a lot of documentation for that available. There are tutorials to get into it. Tom already mentioned about the Jupyter notebooks and so on. So in Python, that's a very convenient way in getting into the topics where we have used a lot of time to get that on a very good level. And we have generic networks available for testing the system. So there's a huge amount of that. So as I said, we have run a lot of validation with commercial software. So we have more than 250 unit tests actually across all the different Panda Power functionalities. So if we have a new release, we run those tests to be sure that it's really validated and that we don't integrate any bugs actually in the software. So here's just a very short example how that looks like. So it should somehow bridge maybe the barrier of saying, well, I can buy a commercial software, I have some GUI, and then I can work on that. So here we are not using a GUI to design the grid, but actually it's a command line way of scripting with Python. And so at the very first step, so we help very much with the tutorials to get into it with simple examples. And as you can see, it's a very easy way to develop a grid. So you just have to define that you have an empty network, then you define the buses with certain parameters. then you can create elements connected to that. So for example, load, and you can then integrate a transformer and a line. And so including the data that you can get from data sheets data, we have an element model. So we are not talking about an impedance model that is often used, but an element data model, which means we just need to integrate to give the parameters for the elements, and internally we calculate the impedance model of that. So this is really very convenient for the user to get into it in a very easy way. So if you run with this simple network a power flow, just type in pp point run pp of the net, and then you can print out the results coming from that. So you directly see then what is the transformer loading, line loading, voltage vector, and so on. So you can do a detailed result analysis of each element. So for each element, we get the Panda tables as a result. And so it's very easy to get access to all this data and compare and run additional analysis on that. So this is a very brief glimpse into how to get started, and I think this easy example shows that it's not complex. It's easy to write and very convenient. So the hosting capacity is one of a huge number of different studies we can do with that. So I selected that because it's very easy to understand, and it brings some ideas of that. So if you look at that distribution grid here, you can see that there are photovoltaic connection points. We have installed PV plants, and we have connection points where we can install additional PV plants. And so now the question is, we don't know where the PV plants actually occur in the distribution grid. So we can guess that somewhere there will be up here. We can guess how much power will be installed, but we don't know exactly where it happens. And that this is a really relevant question going into probabilistic analysis is given here. So you can see that if we run the analysis, depending on where the installation actually takes place, then we can see that there is a huge difference how many PV plants actually can be installed, because of course installing near to the transformer allows more hosting capacity than it's at the end of the feeders, causing voltage issues. And so depending where they are installed, we get a large difference with regard to the installable number of PV plants. If you look only at one calculation, you only get one number, and this is not the reality. So it could be from 8 to 15 in this little example where you see the difference here. So also here, so you have it in the paper and so on, so to have a more detailed view on that. So to run this hosting capacity is just this little code. So we can easily, so we import the input data, we define the results actually, and then we can start with a while loop and identify, we install additional plants as long as we don't get any violations. And so this is very, very easy to use. And so we include, of course, line loadings, transformer loadings, and voltage violations. So they are here in this function of violations. And so what we get is then a distribution of the plant size that can be achieved applying this to the specific grid. So we not only have a distribution of installable capacity, but we also have a distribution of what are the violations. So are they transformer loading? Are they line overloading or voltage violations? So this is very important to analyze the grid with regard to what kind of technologies could be applied to maybe extend the hosting capacity in there. So we have run things like that on huge number of networks. So here we have done that for a Swiss distribution system operator, Monde Energie, where we have analyzed 111 networks. We were analyzing what is actually the expected installed PV capacity. So you see that here in the red bars. And so we analyzed the additional hosting capacity the grid allows. And what we can see that these grids are quite strong. So even with the increase until 2035, only few of them have a lower limited hosting capacity compared to the expected additional PV installation. So they don't have to care much. In other grids, it looks quite different, actually. So we can also apply that then analyzing different smart grid technologies. So here, for example, if we have a base case, so we just don't do anything, then we can apply peak shaving, we can cosine phi reactive power, we can make it active power dependent or voltage dependent reactive power, and we see how it is possible here with one example to increase the hosting capacity in the system. Another study could be done on layout, tap changing transformers, for example, and a combination with other strategies, so that it's a combination. And we see that we can increase hosting capacity in this cases more than 200% actually. So this is an easy way to show what is possible. Also another study here done for Bayernwerk with 300 low voltage grids, where we analyzed the hosting capacity. We're analyzing the full roof potential actually that is expected. And if we consider the full 329 low voltage networks, we have identified that only in 85 of them, so you see that here, we have voltage violations. In others, quarter of them, the full PV rooftop potential can be used. In 30% of them, it's easy just to exchange the distribution transformer. So that means it's not a big deal. Then we have some overloading issues. And so going into on-load tap changing transformers, it's a voltage-related issue. So we consider those quarter of the grids in more detail. We are analyzing them, so you see them distributed here. And we can see that next to the already installed PV capacity, as you can see here, so there are already grids with a very high capacity of installed, so already 800 kilowatt, for example. We can see that there exists in green a remaining hosting capacity, and by installing the on-load tap changing transformer with red, we can increase that further on. And in some grids, we have still a potential for additional power to be installed, so the rooftop potential is not yet, there's still room there. So if we analyze this, so we can see that with the on-load tap changing transformer, that in 1/3 of the cases, the full potential can be used. Then there we have limits with regard to the transformer size. And then we have one quarter where we still have voltage violations, and another quarter where we have line overloadings, and so we have to use other solutions. Finally, it's grid reinforcement, for example. So coming to a brief overview, so the idea of this presentation was to give you a small introduction on Panda Power that was published actually not 1 year ago, so it already attracted a huge community there, so it's very dynamic at the moment. We have already, it is already deployed in multiple projects worldwide, so not only from us, but also in other institutions. And you can see many presented examples available in these interactive notebooks, so you can get into the topic very well. So we have applied Panda Power in with more than 10 distribution grid operators already. So we are running at the moment a very large study, also with 10 grid operators, where we are doing automatic optimization, grid reinforcement on all voltage levels. So this is a very exciting project at the moment. And this allows to pave the way for power system transformation, looking over the next 10 to 20 years, a very exciting one. And so I was just presenting the hosting capacity example. And yes, so having said this, a huge amount of information is available in the given links. And I would be happy to increase user community and maybe also applicable in the Indian context. And so I'm looking forward for further discussions on that. And if you need any help, just get in contact. Thank you.